Good morning, this is Dr. Turner for Integrated Math 3. Today we're going to be covering Unit 3.6, which is binomial expansion. Technically, by now we've already taken our Unit 3 test. I try to keep 5 standards in each unit, and sometimes some are a little bit bigger, some are a little bit smaller. So we're going to tack in 3.6 onto our Unit 4 test. This is a fairly straightforward section, so it shouldn't be too bad. You'll see what I'm talking about here in just a second. So this ties back into polynomials, and we looked at all kinds of things we can do with polynomials in Unit 3. We looked at adding, subtracting, multiplying, dividing, factoring, solving. And so binomial expansion is kind of an expansion of that. This really more is like distribution, but you'll see what I mean here in a second. So to start out, we've kind of already seen binomial expansion. If we look back at our perfect square trinomials, a plus b quantity squared, recall that that was a squared plus 2ab plus b squared. And the idea behind that is that rather than having to do FOIL, in this case for a quadratic, it's giving us a shortcut so it's a little bit easier. Similarly, if I change this to, let's say, a plus b quantity cubed, I could do a plus b times a plus b times a plus b, but because I'm doing a binomial times itself 3 times, I end up with a total of 8 terms, and that can be a little bit overwhelming, especially when you get down to, let's say, a plus b to the 5th power. 2 to the 5th power, that would be 32 terms that you'd have to go through and very carefully sort out and identify what are like terms and what aren't. So, rather than doing that, we do have a shortcut here for binomial expansion. There's a more sophisticated way to do it that we'll talk about second semester when we get into our statistics unit. But for now, we're going to be using what's known as Pascal's triangle. You may be familiar with Pascal's triangle. What happens is that we start out with a 1 here on the top, and then we do 1, 1. And then we have 1, 2, 1. And so every row down from here, we are going to be adding the 2 numbers that are immediately above it. So for instance, this 2 I get by adding 1 plus 1. And then we'll continue to fill in the rows. So always 1's on the outside, 1 plus 2, 2 plus 1, and 1. And we can keep going, 1 plus 3, 3 plus 3, 3 plus 1, 1 on the outside, so on and so forth. So this is something that's taught in pattern recognition, typically in middle school. And if it's your first time seeing it, that's okay. I'm just kind of filling out a couple of the rows here for us. And each of these, again, what I'm doing is I'm adding the 2 numbers that are immediately above it, which I'll point out here in just a second. Let's fill in one more row. So any of these numbers I pick, let's say 20 for instance, I got by adding 10 plus 10. And 21 I got by adding 6 plus 15. And the 5 here I got by doing 4 plus 1. So that's true throughout the whole Pascal triangle, and you can continue to go. Well, why is this important? We start recognizing patterns when we're doing these binomial expansions, and rather than have you prove it, I'm just going to show you how this looks. So when I have, let's say, a plus b quantity cubed, and I ask you to expand this out. Just like with a plus b quantity squared, if you're looking at the exponents, notice how the a terms go from 2 to 1 to no a term at all. And likewise, the b terms increase. There's no b term, and then there's a b, and there's a b squared. We find that that pattern holds true for any binomial expansion. So if I had a plus b quantity cubed, my a is going to start at 3 and it's going to go down from 2 to 1 to nothing. And my b term likewise is going to go, but it's going to go in the opposite direction. So I start with 0, and then b to the 1st power, and then b squared, and then b cubed. So we're trying to write out the expansion of the binomial without having to actually do 2 by 2 by 2 and get 8 terms. Okay? So that's the pattern for my values, a and b, but I'm missing coefficients. Well, our coefficients come from Pascal's triangle, and we'll talk about why that is second semester, but for right now, we just want to be able to identify what the coefficient should be based on this triangle. At the top here, most textbooks are going to refer to this as the 0 row. And then past that, looking at 1, 2, 3, 4, 5, 6, so on and so forth, if I want to know what the coefficients are of my binomial expansion, I just look at that row. Let's say in our case here, a plus b quantity cubed. And I made my numbers a little too big here. Let's adjust that. So they're lining up 0, 1, 2, 3, 4, 5, 6, 7. That's a little bit neater. So if I want to expand a plus b quantity cubed, I'd look at the third row. And that tells me what my coefficients should be. So over here, I have a cubed plus 3a squared b plus 3ab squared plus 1b cubed. And so on and so forth. If I do a plus b to the fourth power, to write it out, my a powers are going to go down. You want to leave yourself a little bit of space here. Your b powers go up. And then you just have to fill in the coefficients. Here, this is a plus b to the fourth. So I'm going to take this fourth row here, 1, 4, 6, 4, 1. And those are my coefficients. 1, 4, 6, 4, and 1. And this pattern will hold true for any of these. Again, you can do it out if you want. If you forget the pattern recognition, you could multiply it out. But by the time I get to, let's say, a plus b to the 7th power, that's 2 to the 7th power. That's 128 terms that you would have to combine like terms with. So these are always, like the other formulas we've learned, always meant to be shortcuts. Okay. A to the 7 would be a big one, but still doable. So again, a goes down. Try to leave myself enough space here. And then b goes up. 0, 1, 2, 3, 4, 5, 6, and 7. So just like before, I'm going to go through here. I'm going to look at my 7th row, and you could go higher than that. I just included 7 for our purposes. I don't think I gave you anything higher. So look at the 7th row, and those are my coefficients. So 1, 7, 21, 35, 35, 21, 7, and 1. So this is all very formulaic, how you expand the formulas. In practice, I'm going to give you problems that are asking you to actually evaluate these. And I'm only going to do a couple here for the video. We'll do more in class, but let's start with something simple. Let's say x plus 3 to the 4th power. So now I have x for a, and I have 3 for b, but it's the same process. So I'll go through and I have x cubed, and you can do it like I've been doing it if you'd like. X squared, x, and then the constant. Then for my b, my 3 here, there's no 3, times 3, times 3 squared, times 3 cubed. This is a 4th degree, so looking up here, I have coefficients. Oh my goodness. Well, that's okay. I was looking at x plus 3 quantity cubed. We'll just fix that there real quick. So I'm looking at the 3rd row. I'm going to do 1, 3, 3, and 1. So that's basically our answer, but we want to clean it up. So here I do 3 times 3. Here I do 3 squared times 3. And then 3 cubed. That's basically it. You expand it out and then you clean it up. Let's do another one here. Let's do x plus 5 to the 4th power. So starting with the 4th power here, I'm going to go 4, 3, 2, 1, 0, and then 0, 1, 2, 3, and 4. And if you need a calculator for these higher exponents, that's fine. Fill in your coefficients. This is a fourth degree polynomial, so I have 1, 4, 6, 4, and 1. Now it's just a matter of the arithmetic. 5 times 4. 5 squared times 6. 5 cubed times 4. And then 5 to the 4th power. So that is your binomial expansion. Now, if I made this, let's say, x to the 10th power, x to the 20th power, that's a lot to have to do, and that's why we're going to learn another way to do it so they don't have to write out the Pascal's triangle every time when we get to our statistics unit. But for now, I just want you to use binomial expansion with the Pascal triangle, be able to tell me what the coefficient should be based on the row, and then to clean it up like we did here. That's all for today, guys. If you have any questions, please reach out to me. Otherwise, I will talk to you soon.